Okay, so I'm Dominique Weis. Thank you for the invitation. Thank you for the Peter Wall Institute. And today, I'm going to talk about magmatism in the Cascades, subduction zone in the Pacific Northwest, and what do we learn? I'm a geochemist, so what do we learn from geochemistry? And also about the whole subduction zone. No, this thing does not work. So I'm going to give you a brief introduction of subduction zones, the focus on the Cascades arc, and I'm going to talk about the High Cascades, which are in the US, and the Garibaldi Volcanic Belt, which is in Canada, and then geochemical analysis. What you see up there is the Mount Baker view from Vancouver, BC. It's 50 kilometers south. It's a gigantic volcano. It's not the biggest one. The remote does not work. That's okay, I can keep pushing. The subduction zones are actually the Earth's biggest recycling center. And it's important because new continental crust is generated in the subduction zone. Surface materials are subducted deep into the mantle, or not deep into the mantle, and the cascade arc is up here. So we call this the ring of fire, and I learned out today that this red light that we see around IPGP is actually the ring of fire. The ring of fire contains 75% of the Earth's volcanoes, 90% of the earthquake. So it's very significant tectonically. What's happening in a subduction zone? Why do we melt the mantle? And why is this important? A key parameter is water. We need water that reduces the mantle solidus temperature. We also have additional melting here in the core, and we modify the crust. We do the dehydration happens, melting, and we generate volcanoes. Related questions are how much water is carried down, how much of the subducting mantle lithosphere is hydrated, and how much sediment is subducted versus added to the accretionary wedge. So either sediments can be brought down with the subducting slab, or they can accumulate here. So the dehydration may be completed at very shallow depth. And today we're going to talk about a very hot subduction zone. So what are the implications of this? And when it's melting, are we melting depleted upper mantle? So the same as the MORB source, the mid-oceanic rich basalt source? Or do we have evidences in our magmatism of deep mantle components at hot spots? So we talked yesterday about Hawaii, which is the typical example of mantle plume volcanism. And what you see here is Mauna Kea view from Haleakala. It's a big volcano. We talked about that yesterday. And all these oceanic islands, and Hawaii in particular, have different isotopic signature, the signature of the deep mantle. Now the question is, are we seeing this in the subduction zone volcanism? So we talk about using the fingerprint of the mantle. Signature de la source. Alors, ce que je veux, signature of the source. What I want to show here is the difference between the upper mantle, the arcs, and we're not going to talk about the mantle anymore, except using the hand member. So the comparison in this LED diagram, and so it's a LED diagram. So it's the same chemical element, which means that when you mix two components, you're going to end up with a straight line. So what we have here is a comparison between island arcs, so we are in the oceans volcanism, and continental arcs volcanism. You have here mid-oceanic basalts in, so upper mantle in black, and your island arcs. On the continental arc side, you can see that you have a lot more noise. And this noise is simply showing that you have different components than the upper mantle. You have some, first you have mixture, that's in the source, but then you can incorporate sediment and continental crust, and you see that you have way more here in the continental arcs. Okay, let's go back to the Cascades. We are in the Pacific Northwest. And what you see here, we're following the Cascade arc along the coast of British Columbia, Washington, and Oregon, and it goes to northern California. That arc is 1,250 kilometers in length. The width can be as small as 25 kilometers to wider than 100, and there are 2,800 quaternary volcanoes. I make a distinction because you have quaternary volcanoes, but you also have what they call the ancestral cascades that have much older volcanoes. There are 30 high peaks. Now, it goes from 30 kilometers north of Meager up here to 25 kilometers south of Lassen. The Juan de Fuca plate here has been subducting for about 40 million years. And as you can see, just in geography, again, we have two different segments. The High Cascades in the US, which is basically north-south, and the Garibaldi Volcanic Belt in Canada that is following an angle along the subduction zone. It's a hot subduction zone, and the only other subduction zone in the world that's comparable is Mexico. I wanted to show you what these volcanoes look like. And what you have here is Lassen. So we're going to go from south to north. That's in June. It's a big peak. That's Shasta and Shastina. That's the largest by far. That volcano complex is twice as large as any other one. You have Crater Lake, which was exploded under the name of Mazama. Mount Hood, which is very prominent above Portland, but is actually a very small volcano. Then Mount St. Helens is also not very big. It had a very big explosion in 1980 and something, very explosive, but it's not a very big volcano. And then Baker, where you can see that all these volcanoes are more or less dormant. You have some fumaroles activity on the summit here. So you can see, and that was the purpose of the Google flight, that in the US the volcanoes are dispersed, and then as you go north, they bumped into each other. Big activity. That's activity in the Pacific Northwest in the past 4,000 years. And basically, every single one except Crater Lake and Mount Jefferson, all these volcanoes have erupted. I'm afraid that the Pacific Northwest has serious problems in terms of volcanic risk, because no matter what, one of these volcanoes will explode. So it's also a big earthquake risk. And one example of this whole activity is the Olympic Mountains, which are off the coast of Seattle there, basically correspond. This is not volcanic, it's just sediments, it's accreted. So the question is, how much of these sediments have been subducted? And this gray zone here seems to, it's interpreted from a geophysical modeling. That's the accreted section along the Cascade zone. So the big question is how much of these sediments have been incorporated in the volcanoes. You can see different seismic profiles across Cascadia. the slab, so what's going down is dehydrated below the volcanoes. And what we see is that there is 0% of sediment subducted on Vancouver Island and down to 50% in Oregon. I don't really have an explanation why that happens. I'll show you why we can say it's happening, but it's a big difference. Now, I keep saying that the Cascades are a hot hack. What does it mean? We have a pressure versus temperature diagram here. The color codes here of the PT paths for the slab surface are reflecting what's on the map. Don't try to figure out. The main point I want to show you is that the orange and the gray here, Cascadia and Mexico, are by far the hottest subduction zone. Now, what does it mean, the hottest? There are many reasons for that, and reasons we don't know too. One interpretation might be that it's very hot because, for instance, up north here, the subducting plate is very young. You can see that the explorer plate is not older than 4 or 6 million years. One other important parameter in the geography is the presence of this Nootka fault, which is, in the past, Explorer and Juan de Fuca were the same subducting plate. They broke apart. And that's an important point. We'll come back to that. And then there's another plate here that is smaller, the Gorda plate, basically at the level of California. Now, in terms of composition, and that's the only slide I'm going to show about composition, what rocks are we dealing with? We're dealing with 3 types of primary magma. We have this high aluminum olivine tholeyite, which in a silica alkali diagram plot here. We have some calc-alkaline basalts, and HAOT are mostly present in the High Cascade. The calc-alkaline basalts are present everywhere, and then we have a series of much more alkaline rocks in green here that basically dominate here in British Columbia. For those of you who have a petrology background, what does that mean? Can somebody help me so that everybody stays awake? No? How do you go from those compositions to these compositions? Lower degree of partial melting, higher pressure. Now, the correlation between these rock types and the segments based on early studies of isotopes, there was none. But the work of Anita Granter and one of her students, Schmidt, documented the northern segment, so from Meager to Glacier Peak, the Columbia segment from Mount Rainier to Mount Jefferson, the central part of the Cascades, which is basically the three sisters all the way to Medicine Lake, and then the southern part in California, Shasta and Lassen Peak. Now, what could distribute the composition and the different basalts? The first is the age temperature of the slab. Again, you can see that the subduction slab is very young, 10 million years here, younger there, younger than 3 or 4, so it hasn't had the time to cool much. There is a gradient in the sense that this is younger than here, and by definition it will be hotter. The other thing, there are slab gaps, like the Nootka fault. Another question is, what material came from the basin and range mantle, and do we see an ancient subduction signature? That's mostly true in the southern here, in California, also accreted mantle domains. And there are 3 major accreted domains. There is the insular superterrane in British Columbia, the Siletz terrane here in the middle, and the Klamath block. So those come from earlier subduction zones. The bottom line is it's a very complicated setting. But no, they're all way older. Don't ask me the detail of the age, but they're old. So I had always said, I don't want to work in subduction zone. It's too complicated as a geochemist. And it all started with a couple of my postdocs. One was actually a previous student of Catherine who wanted to work on sediments. Another one wanted to work. She did her PhD at the University of Washington in Seattle, and she wanted to continue working. So it all started with her doing a study of Mount Baker. And you can see that Baker has about 10,000 years of activity, different phases, different forms of volcanism. And what did she find? Again, and we're going to see a fair amount of these LED diagrams. We have the subduction zone, the oceanic crust subducting here, Juan de Fuca, Gorda, and Explorer. The Mount Baker basalts plot here, so they don't have a pure upper mantle signature. It's not too surprising. And what we have here is the northern Cascadia, so the sediment up just north of Mount Baker. And the interpretation is that these Mount Baker basalts represent a mixture between the subducting crust and some of the sediments.
What are data that has a lot of scatter? Is that just older data?
Yes, I'll show you.
Okay.
Good question. The trace elements show the typical, so what we use here is all the trace elements organized by order of incompatibility. We have our samples normalized to MOB, so upper mantle is plotting just horizontally, and this yellow zone is what's called the subducting component. Also characteristic is this trough for niobium and tantalum. So that's all basalts from Mount Baker, and the question is how much sediment has been incorporated in there. And basically what Emily did for a PhD was to model the various components. I'm not going to take you through all the details, it's no point. Calculating all this mixing, it's basically, she calls it a dog's breakfast. And the point is that you can model the relative contribution of your components, assuming you make assumptions. The assumptions are the input data into the model, and then the different phases of volcanism on Baker's shows you that you have, in this case, 5% of partial melting, a little bit of sediment, 30% of partial melting, and also some sediment. Not that much. But so that was a study on Baker. How can we apply that to the rest? So the first part of the work was studying the Garibaldi Belt. And the question is, so we're up here, do we have less slab input? You can see here in this trace element diagram that the Garibaldi Belt doesn't have this typical trough for niobium and tantalum. It also basically almost a MOB composition. Same thing, modeling, that's not the point. It's only, what's interesting though is that when you look at these curves in the Garibaldi Belt, it's basically the same as Mauna Kea. There is no sediment component. So when you cross the border, the Canadian volcanoes, I like to joke about that, are not contaminated while the Americans are. But how can we explain that? So we went back, we did more study, more sampling, and as much as I like the outdoors, there was no way I could go do that. So we had a bunch of our students who were very keen on climbing. We paid them, we gave them the department truck, paid for the renting, and they went and collect. They did 3 weekends and were very happy collecting these samples. So precision, accuracy of the data. So we see this difference between the Garibaldi and the High Cascades, but one of the first questions, except for Mount Baker, all the high cascade data was old data. And so the first thing we did, again, I swore I would never do something like that, but we reanalyzed 37 samples that had been previously analyzed in the 90s. And you see the difference. It's not major, it's not big in strontium, but even in neodymium is very big, and I'll show you in a second the difference in lead. And then we got new samples, and same thing in the Garibaldi Belt. For that, we use an instrument where I work, the Pacific Center for Isotopic and Geochemical Research. We use clean labs, and I'll talk more about the clean labs, and our clean is clean next week when I talk about honey. But what do we show? That's the old data in the Cascades by Bacon et al. In 97, and that's data for 5 volcanoes, and that's what I call the potatoes, because if you do a field around this, you'll have a potato. Now, exactly the same sample, we reanalyzed them with the multi-collector. It's about 10 times better, and you see a structure. The first thing you see first, you can do a best fit line among all the high cascades, except 3 samples from Mount Adams, and that best fit line is going between something here and our Cascadia sediments. We'll come back to that. Adams is slightly different. It's quite interesting. Now,
so the old data were all Tim's data?
Yeah. Tom Sisson, we analyzed also some samples from Mount Rainier, and those are the diamonds here, so part of the high cascades. It's entirely coherent. That's pretty much fun to see. Now, new data on the Garibaldi Volcanic Belt, so we cross the border and we go down. The Garibaldi Belt doesn't fit on this mixing line here defined by the high cascades. It's quite interesting, except Glacier Peak, which is both at the hinge geographically, but also isotopically. It's quite fascinating. So, there is less to no sediment input up north. Now, what we did, is model the various compositions. We define a depleted mantle end member and a sediment end member. Basically, the depleted mantle is here. The sediment end member is the average of these. And the high cascades, which is quite surprising because it's about 1,000 kilometers, all the volcanoes basically plot on this mixing line. For the Garibaldi Belt, we are further below. And we didn't rerun the Gorda samples, but we rerun some of the Juan, the Fuca upper oceanic crust basalts, and that's where they are instead of having this potato as before. Yeah. So what's also interesting is that, and sorry for the resolution here, the Cascadia sediment, so that's the postdoc of Marion Carpentier, is here. That's an end member that fits in the mixing of the high cascades and the depleted mantle here. The Astoria fen sediments, that's a study of Julie Pritulak, are more radiogenic, and they don't intersect this mixing line. And the interpretation is that this fan of sediments is too young. What has been brought down in the subduction zone to be incorporated in the volcanoes is probably 30 or 40 million years. Because geographically it doesn't make any sense. We see that end member in here, but we don't see sediments that we can sample today in the Astoria fan. Same thing with other isotopic systems. In case you were not convinced, we have here high cascades and the Mount Adams high aluminum olivine tolleites, and mixing between the Juan de Fuca, the sediments, and the Garibaldi Volcanic Belt is quite different. So, and Glacier Peak initially was thought to be part of the Garibaldi Belt, it actually belongs to the High Cascade trend. So that's quite interesting. The bottom line is that this trend here that we see in the Garibaldi Volcanic Belt is actually going towards composition of Mauna Kea, the average deep Pacific mantle. The question is, how does that happen, and how can we say that? I'm going to take you through this through geographical trends. So we have radiogenic lead here, and we go from Lassen all the way to the north. And what we see is that basically, and that's what's reflected in a lead-lead diagram, all the high cascades are on the same trend, and there is basically no variation, or very little variation, in the radiogenic lead. When you go to Canada, you cross the border. It's actually quite funny that it corresponds to the border, basically. You start to see a decrease of these values. It's a very distinctive composition. And for those of you who will come next week on Tuesday, I'm going to show you how we use this trend to trace the obsidians that were used by the First Nation in British Columbia. It's a very distinctive signature. Same thing with epsilon hafnium. You decrease, you have more or less a depleted mantle composition up here, and you go towards more enriched values as you go north. Same thing in trace elements, zirconium, niobium, for instance. Here at Glacier Peak, decrease as you go north. A couple of other ratios. What this documents is that basically as you go towards the north, so further into Canada, you have less slab contribution. And interestingly, in alkali silica diagram, you basically migrate in this direction. So again, your composition are more alkalic, potentially reflecting deeper, higher pressure of melting and lesser degree of melting. Now, modeling this data shows this. It gives you a trend in temperature with a difference of about delta T of 200 degrees as you go in the north, and an increase in pressure of about 2 GPa. That's not, that's very significant. You also have here 1350 is the limit, the maximum temperature of the mantle wedge. So how can we locally increase the temperature so much and increase the pressure?
How do you know the mantle wedge temperature?
That's modeled on the basis of that's Michael Bostock work. It's a geophysicist modeling. So we go back to the map and the geography. And Catherine, I hope this map is good for you.
Yes.
What we have here is this Nootka fault. So you use separating the Juan de Fuca plate from the Explorer plate. And it's a big fault. And the volcanoes, the location of this fault corresponds to where the volcanoes shows this different mantle signature in the basalt. And our modeling is the following, is that, so we go from south to north, you have this, and you also have a very big difference in the depth of the subduction zone. You have a wedge here that allows some material that melted from further down to come up, upwelling through the slab and flowing south. So it is a mixture between a deeper mantle component, and I didn't want to go into all the details of geochemical modeling, but that component corresponds to the end member of Mauna Kea, which is the average deep mantle in the Pacific. And so the interpretation, this is just deep mantle from average mantle from the Pacific that's melting and coming into this mantle
What do you think, this is a morph type mantle, or do you think it's a plume type?
It's a plume type mantle. So it's coming from deep enough. No, it's not morph at all. I mean, at least in terms of trace elements and isotopes. And then to explain the trend from south to north, some of this mantle flow is drifting to the south. The geophysicists are seeing this, the tectonophysicists are seeing this, and that's how it works.
Is this a little bit analogous to like Mount Etna?
I don't know the geography, what's happening on Mount Etna.
You have sort of an OIB type chemistry
Yeah.
in the middle of a subduction environment, and people have been puzzling. It reminds me.
Oh, that's cool. That's cool to know.
Yeah.
Yeah. So what we have here, and that's the conclusion of this study, is that we don't have all these subcomponents. We basically have three mantle components in the cascade arc. We have the High Cascades, which is all this, where we have one single depleted mantle component plus subducting sediment, and we have an equivalent up here in the Cascadia basin. What's very interesting is that we have a series of accreted terrains. They don't seem to interfere at all with the geochemistry of these volcanoes. Now this, I can be the devil advocate with my own data, is that this can be a question of mass balance. Huh? But because we working with rocks that have more evolved compositions, and it's harder to change their composition, but still, there's no evidence for influences of accreted mantle domains. And interestingly also, the sediment package is pretty homogeneous. That's completely counterintuitive. The second component is what we see in the Garibaldi Belt, where we have an influx of an enriched mantle. It's not, I think I'm going to confuse the geophysicist here. It's enriched because it's not depleted. It's just the deep oceanic mantle that's coming at the slab edge, the gap. And then we have this single component here in Mount Adams, which is tapping some local heterogeneity. Clearly, we studied 5 of the big volcanoes in the US. We've studied 5 of the volcanoes in Canada. There are many, many more. And looking into finer details, we're probably going to have to refine this model, but it's quite interesting. So to come back to our original question, what components do we have in the arc? We have the depleted upper mantle dominates in volume what's being melted. And only in localized area, in the case of the Cascadia, it's in the Nootka Fault, have we some enriched mantle component leaking. The global implications are that with this geochemical data, we can help the geophysicist modeling the various components. My colleague Michael Bostock, for instance, have been working for decades modeling the subduction slab structure, the amount of water, and this data is helpful. So if you were not convinced, I know I'm preaching to some of the converted here, geochemistry is quite useful. We can see, and at the end of the day, the Cascadia arc wasn't that complicated. I've tried to simplify. This is a relatively general audience talk, but it's not so much of a headache. We see clearly the subduction component. The mineralogy has been determined. We can see mantle flow patterns. And I love the difference between the Canadian volcanoes and the US volcanoes. So I want to talk the team working, and we'll see the team in a second. Emily, who was a postdoc, Marina, who was a PhD student, and then 2 honor students who all contributed to this project. And that's us at Newbury Volcanoes. I want to thank also the sampling team. I can tell you stories on top of doing very dangerous hiking and climbing. They ended up in the ditch. It wasn't their fault. The tires exploded. Yeah, the tires of the truck. We also had a funded program by NSERC, the Canadian equivalent of CNRS. That was a training program, and we had the opportunity to, that's where all these pictures of the volcanoes were taken, to do a trip of 2 weeks. We stayed in various volcanoes, and it was very fun. And that's the team of the lab. So thank you very much. Any questions?